Hi, welcome to Module 5 for the Information Systems Resource Management course. This section we're going to be talking about architectures and blueprints. In the last module, I left you a PDF of a presentation on enterprise architecture, which there is no video for, but from there, that's the starting point for what this is. Architecture has been a relatively interesting area of IT because you don't see the role of the architect emerge until around the late 1990s. Pretty much these were considered systems analysts or designers, of the overall topology, which is like the networks or hardwares or what should go together. Sooner or later, people began to realize that there's a value in having someone who looks at the entire organization and looks at all of the software and basically provides a governance structure behind what is being implemented as opposed to just the developers. And so that's how the role of architecture actually comes into play. What we then find out later on is that as this role evolves, that individual starts to get a higher and higher seat at the table from an IT perspective, to the point where some architects are actually like CTOs of organizations, or they report directly to the Chief Information Officer so that there's no bias between implementations of applications or infrastructure. It is the individual who's responsible for the technology direction of the company. So the first IT architecture, we're talking about hardware. We're talking about mainframes with dumb terminals. The architectures that they had were basically focused all on this is what the hardware looked like. There was no real business process. There was no understanding for how software integrates. It's just what are we going to what are we going to develop, and what's the hardware platform that we own or that we're going to acquire. As many computers come into play, we have departments, but you still have this notion of the master-slave. You may have an individual computer that's dedicated toward finance, or an individual computer dedicated towards, let's say, logistics. These would be like the old Lang VS systems. For those of you who may or may not remember those were actually very good machines. Or the NEC computers, and they had specific tasks associated with them. So those architectures were a little bit different. But again, we're still talking about hardware architectures. So with the microcomputer, we find that we're putting more power at the hands of the local desktop, giving the individual employees the ability to do more. The key here between these architectures is where the processing occurs. On the mainframe and mini computers, we have dumb terminals. So the terminals couldn't do anything. The actual processing has to occur on the computer itself, which is the mainframe or the micro. When we get to the client server, the microcomputer, now what we're talking about is that the processing is done on the PC itself, that some of the processing can be done there. What's interesting is that now, with the internet, we're going back to this dumb terminal concept, where basically the browser is really a dumb terminal, and the processing is done on a web server or an application server behind it. So it's going back to this little bit of a centralization, but even then we can get more distributed, because with the concept of web services, we can actually distribute processing amongst multiple servers to generate the power that we need without creating a bottleneck on a single machine. So what do we have with distributed systems? Distributed systems allow the processing to be dispersed across different physical machines. Now, why would you want this? You'd want this because you want to ensure that one computer doesn't tie up the whole process. If an entire sequence of events is linear, where we're doing task A, task B, task C, task D, and one computer does it, we know that it's going to be in linear time. If, however, we're able to split up those processes amongst 4 different machines, then we can basically theoretically finish somewhere around 1/4 of the time. And there's a lot of research that talks about the best way to do this. You actually would get into things like parallel processing, which can be done on a single unit. So your computer may have, let's say, a dual core or a quad core, or you'll see servers with quad cores, and some people say, well, how many cores are there on the server? And that's the ability for it to distribute amongst the processing amongst the different chips, so the CPUs, inside of the server. When we talk about distributed systems, we'd like to have our finance machine, let's say, our finance server handle certain things, our operations handle certain things, even in a separate system for HR, so that this way, if something happens to the HR system, it doesn't impact anything else. So IT architects will generally look to say, how should we distribute the workload? How should we distribute the software applications amongst multiple machines? Eventually, we started looking at how do we bring them back into a single machine, because we buy these large machines that don't go down or can have a lot of processing, and we can leverage them by virtualizing them and creating these individual virtual servers within the single machine. So we ask questions like, where is the processing going to be done? How are the processors and other devices interconnected? Where is the information stored? And then what rules or standards do we need to implement this effectively? The goal is really to move appropriate processing as close to the user as possible and let other machines handle the work that they do best. If you think of how you're supposed to implement machines, what you want to do is understand the workflow process. And it's very similar to saying we want to do the jobs where it's appropriate. So the operations folks should basically, they have their own process. We want to make sure that the customer has, inventory is close to the customer, so we minimize the time. Well, there's not that much difference in this. Let's say we had a data center for a machine that's located in, let's say, India, and the processing is really done in New York. Well, you have a couple of things. There is a significant problem in terms of the distance that it takes between the server and the client connection, and so there's a latency there. Furthermore, the infrastructure may be a problem in terms of its reliability. So what will happen there is that we want to say, let's get the computer, let's get the servers or the service as close to the user as possible in a reliable infrastructure as possible as well. So architects will start making those types of decisions as well. Now, if we distribute systems, we also get this notion of interoperability, which means, let's say I have a process that does postal code lookup. And so all this server does is lookups of postal codes and gives you and validates addresses. Well, that service could actually be used by other systems like my logistics system or even my accounts payable system or any other system that really requires to know whether or not the address is correct. So two forms of interoperability: communications between systems. So how do we communicate between these systems? And the two-way flow between user applications. So if we have a client server application or we have a PC where you're operating, let's say like a Google Drive as an example. Google Drive has an application that sits on your machine. You drag a file onto that Google Drive or to that folder within Google Drive. Then what will happen is it will eventually sync. That application will sync the file and make sure that there's a copy on the cloud in Google. That's kind of like a two-way flow between the user application where your machine and the server machine are constantly syncing up in touch with each other to make sure that things are correct. So here's an interesting thought. If you look around the classroom and you look around your office, you have a ton of computers. Is every computer being used? Okay. Well, obviously the answer is no. A lot of the computers will sit there idle. People work 8 hours a day, and they're not going to be using those computers 16 hours out of the day. So there's still some downtime for those units. Even if someone's on the computer and they work for 8 hours straight, they don't use the full capacity of the computer. So there's a lot of potential computing time that's wasted. So there's an interesting thought and there's an equation here on this line that says the sum of CP equals the sum of C. And this is an interesting thought about how we can leverage the technology that we have. Can we get the sum of our computing power equal to the sum of our computers? Meaning, can I make sure that I'm maximizing the use of the idle time for some productive purpose? And we do see there are projects out there, these types of distributed projects that do this. So you'll see the SETI project. Some of you may have heard of that. That's the Search for Extraterrestrial Intelligence. And the way that works is they load, the volunteers for a PC will actually load a application on your machine. You download it and it sits on your machine. Now it acts like a screensaver. Once you have the screensaver, now what you can do is when your computer goes into sleep mode, what it will do is it will go and download a data set from the SETI project. Once it does that, it begins processing, and then it will process the information and send it back. If you have millions of computers doing this, you can process large amounts of data. And that's ultimately what this is about. And we see other projects starting to do that, such as the Genome Project and the DNA Project, that are trying to do the same thing. So they're trying to leverage the excess computing power that's out there so you don't need necessarily a large mainframe.